Thank you very much for the invitation. It's a great pleasure to be back to Nottingham. So, as Thomas said, today I'm going to talk about black rings in global anti-de Sitter space, and this is work that I've done with my student Saran Tunyasunubakol in Cambridge, and will hopefully appear very soon. The plan of the talk is as follows. I will start with an introduction to the subject, try to put our work in context. Then I will discuss our construction of these objects, black rings, which is numerical, so I'll explain how we do it. Then I will go on and discuss some of the physical properties of black rings in global anti-de Sitter space, and I will finally summarize and conclude. So if you have any questions during the talk, please feel free to interrupt me, and I'll try to explain in the best way I can. Okay, so let's start with the introduction. So I think that it's fair to say that for four-dimensional asymptotically flat vacuum black holes, we have a good understanding of these objects within classical general relativity, because we have a series of theorems and results which provide a complete classification of these objects within the theory. For instance, we know that they are topologically spherical. They rotate rigidly with respect to asymptotic observers, and this essentially means that they have to move in a direction which is a symmetry of the space-time. And they are uniquely specified by their mass and angular momentum, and they are explicitly known, and they are given by the celebrated Kerr family of solutions. But also equally important for practical purposes, the methods to construct all these black holes are well known. For instance, the Kerr solution is algebraically special, and one can explicitly integrate the Einstein equations. And in fact, the Kerr solution falls into a wider class of spacetimes for which the Einstein equations are completely integrable, so one can explicitly construct all the solutions in that class. But in recent years, we've become interested in studying general relativity, and in fact theories that go beyond general relativity in contexts that go beyond the actual astrophysical one. For instance, we've been interested in studying general relativity in dimensions greater than 4, or with different boundary conditions, and in particular anti-de Sitter boundary conditions, and this is going to be the subject of my talk. But like I said, also many people, including some in the audience, have looked at alternative theories of gravity. And essentially, the reasons are that black holes in this context that go beyond the traditional astrophysical one can exhibit fundamentally new physical phenomena. For instance, I will concentrate in the just general relativity in high dimensions or in anti-de Sitter spaces, but in fact it is true that in these other contexts black holes need no longer be spherical. And the first one to be discovered was the black ring. This is a black hole whose horizon topology is S1 cross S2 in 5 dimensions, so it has the shape of a donut. But in fact, black rings not only exist in 5 dimensions, they also exist in higher dimensions, but they are only known explicitly in 5 dimensions. But in fact, as you go up in number of dimensions, it is possible in vacuum to have multiple black hole spacetimes in equilibrium, and the first example of this was the black Saturn. So the black Saturn consists of a black ring surrounding a spherical black hole. And again, this is known explicitly in 5 dimensions, but it should also exist in higher dimensions. Also, a novel feature that black holes exhibit in high dimensions is that they are no longer uniquely specified in terms of their conserved charges, namely the mass and the angular momentum. So the black ring, for instance, can have the same mass and angular momentum as the rotating black hole, the analog of the Kerr solution in high dimensions. And in fact, there are black Saturns for which they have total 0 angular momentum at infinity. So the celebrated uniqueness theorems in four dimensions do not have a straightforward generalization to higher dimensions. Also, whilst we believe, or many believe, that the Kerr solution is dynamically stable, and that's why the Kerr black hole is important for astrophysical applications, it turns out that we think that generically black holes in high dimensions should be unstable. The endpoints of these instabilities are not known, but I think that's a very interesting open problem because they could lead to counterexamples to long conjectures, so long-standing conjectures in the field, such as weak cosmic censorship. So this is, of course, I have nothing to say about this in this talk. This is indeed the subject of another talk, and hopefully we'll learn something in the near future.
Is there an intuitive reason to understand why theorems of general relativity in 4 dimensions don't work in more than 4?
The uniqueness theorem.
Yeah.
Well, so there is an analog of the uniqueness theorem in 5 dimensions for the case where you have 2 rotational symmetries. And the way you see this is that apart from the asymptotic charges, you've got new pieces of data that uniquely specify the solution, and those do not correspond to any conserved charges. So these are geometric. This is geometric data, which specifies, say, the shape, but of course that's something which is not measurable at infinity. So in that case, we know exactly what is the extra data that we need, but in the general case, we don't know what uniquely specifies a black hole. And it's quite likely that, the conserved charges are not enough. So something that's a conjecture is that in order to have uniqueness, one should perhaps incorporate the property of dynamical stability, because many of these black holes which break uniqueness may not be stable. So there's a conjecture which says that there should be a unique stable black hole with, say, this mass and this angular momentum. But that's not known whether that's true or not.
So how does this uniqueness picture fit in with a compactified scenario? So we compactify down to what's got some high dimensional GR scenario. So presumably non-uniqueness theorems are either now compactify down to 4 dimensions. So I have a compact direction.
Well, in this case, we are talking about asymptotically flat spacetime, so they are not Kaluza-Klein type spacetimes which you would then compactify. So I'm not aware of any now example on top of my head for which you can. Sorry. No, that's not true. So actually, there are rotating Kaluza-Klein black holes in 5 dimensions, but for those you have uniqueness, at least of the ones that I recall now. But like I said, I think it's.
What do they look like when you
when you compactify, it's just charged black holes with a scalar field.
Okay.
And yeah, because like I said, in 5 dimensions, right? So with Kaluza-Klein type boundary conditions, there are sort of no non-topologically spherical black holes known. So for the ones that are known, they are uniquely specified in terms of the conserved charges. So rotating spherical black holes fall into 2 families. There's a rapidly spinning and the slowly spinning, and they are kind of separate families. All right, so let me just, because we're going to talk about black rings here, so let me just show to you what's the phase diagram of asymptotically flat vacuum black holes in 5 dimensions. Because in vacuum, the Einstein equations are conformally invariant. One can just fix a scale, and it's commonly, so here, one way to do it, among others, is just to fix the total mass. So once you fix the scale, then you can ask what black holes there are. And one way to show the various families of black holes is to plot the area of the horizon, or the entropy, if you want, against the angular momentum. So for single black hole spacetimes with compact horizons, again in the asymptotically flat context, we have the spherical black hole. The spherical black holes are essentially given by this curve here. So Schwarzschild sits there, and all along this curve you have the generalization of the curve solution to 5 dimensions. And this family ends here at an extremal well, it's not a black hole, that's a singularity. So that's different from the situation in 4 dimensions where the curve family of solutions ends at extremal black hole which has a regular horizon. So that's not true in 5 dimensions. So apart from the spherical black hole, we have deep black rings. So these are given by represented in this phase diagram by this curve. So rings fall into 2 families, which are called thin and fat, depending on the relative ratio between the thickness of the sphere, of the 2-sphere of the horizon, and the size of the hole in the middle. So fat rings end at the same singular solution as the spherical black hole, but thin rings can have arbitrarily large angular momentum. So, as you can imagine, in many areas of physics, when you have large separations of scales, this usually signals the possibility of there being instabilities, and that's in fact what's expected to happen for these very thin rings. So these fat rings are also unstable, but that's a different kind of instability. So it could well be that this new phase, they're all unstable. But like I said, this is an open problem, and it's not the subject of this talk. So
the thin ring seems to have higher entropy than the corresponding black hole.
yes, that's right. Yeah, but well, the fact that has high entropy does not necessarily mean that it's stable.
No, but it might suggest.
It's unclear because so it depends on what kind of instabilities you're allowing for. So if you look at perturbations which do not break the rotational symmetry, then it's possible that this black hole sitting over here can evolve into these black rings here. But if you break the axial symmetry, namely then these black holes may just emit gravitational waves which carry angular momentum and may settle down to another spherical black hole with lower angular momentum. Because you always have this sort of family of solutions over there. And these, in fact, in 5 dimensions, these spherical black holes, there's been analyze the gravitational perturbations which break the rotational symmetry, and they are shown to be, well, the analysis of perturbations hasn't found any instabilities. However, some Japanese group did a nonlinear evolution and they found an instability. So these should definitely be unstable under Gregory Flamm, even though on this sort of part of the phase diagram, this is the only solution, but clearly this just looks like a boosted black string, which is, and so in this case, because the Gregory Flamm instability is a fast one, because it's an exponential mode, the emission of gravitational waves, so Gregory Flamm here would just break the axial symmetry, but that's an exponential instability. Gravitational waves can carry away angular momentum, but they're not very efficient in doing that. They're only sort of, they do it through a power law. So it's quite likely that these things will break. But yeah, but the fact that they have high entropy do not necessarily mean that they are stable. Okay, so I think the study of black holes in anti-de Sitter space is also interesting just from the point of view of general relativity, because it turns out that many of the classical results on black holes do not hold in AdS. For instance, it's no longer true that even in 4 dimensions, AdS black holes have to be spherical. There are examples, which the horizon topology is that of a plane, or even a hyperboloid. Uniqueness, we don't have a uniqueness theorem in AdS, which is analogous to the one in flat space. So we don't know. Fewer symmetries, it is quite possible that in AdS there are stationary black holes with a single stationary killing field. That's hard to see how it can happen in flat space, but in AdS, why not? Instabilities, apart from the instabilities that may afflict black holes in asymptotically flat spaces, of course in AdS you've got the boundary, which is time-like, so you have reflective boundary conditions, and in fact AdS itself has been shown to be unstable, so there might be some new dynamics related to instabilities of black holes in AdS, which are different from flat space. So clearly the physics of black holes in AdS can be much richer than the physics of black holes in flat space. But there's one problem, which is that the methods that are known to work in the 4-dimensional or even 5-dimensional asymptotically flat case do not work in AdS. So even with these symmetry class of solutions that I mentioned before, for which the Einstein equations are completely integrable, this doesn't seem to work as soon as you introduce a cosmological constant. Whether it can work or not is not known. So if we want to explore the physics of black holes in AdS, we need new methods, and what I'm going to use in this talk are numerics.
Do they work in DS?
No. It's the cosmological constant screws up thing. Of course, another motivation to study black holes in AdS is the famous AdS-CFT correspondence. which in this context states that stationary black holes in global AdS encode properties of equilibrium finite temperature states of n equals 4 super Yang-Mills on the Einstein static universe, on a 3-sphere, at strong coupling. So black holes know about strongly coupled gauge theories. So this, of course, raises some questions. So firstly, can we have non-spherical black holes with compact horizons in global AdS? This seems to have an obvious answer. That's yes, because a small black hole in AdS we shouldn't really care about the cosmological constant. So the question is really, can we have large non-spherical black holes with compact horizons in AdS? So that's the question that we'll try to answer in this talk. So if they exist, because they correspond to states, equilibrium finite temperature states of a certain CFT, what is the dominant phase? Is this spherical black hole or is it black ring, if it exists? And is there any observable in the field theory which can tell us about the topology of the black hole that sits in the center of space-time?
You expect them to be unstable, right? Or not?
It's not clear. Well,
so
if I tell you the answer now, then you can just leave the room and that's it.
There's this generic argument about reflecting other conditions and gravitational waves exploring all configurations.
Well, so there are different notions of stability here, but so that's what you it's the kind of instability you're referring to is a nonlinear kind of instability, and the endpoint in the presence of a black hole is unclear. Well, for various reasons I can talk about later. So so we are entering the nonlinear regime of gravity in AdS, and I don't think we have a good intuition. So it can go either way. Right. So like I said, so is there any good observable in the field theory which can immediately tell us about the topology of a black hole? Or in other words, how does the field theory explore or know about the topology? So I'll try to give some partial answers to some of these questions in this talk. So before that, let me just explain you how we managed to construct these solutions. So we want to solve the Einstein equations in the presence of a cosmological constant, but for what I will say, the fact that there is a cosmological constant doesn't really matter much. So if you choose your favorite metric ansatz and you plug it into the Einstein equations, then you find that the Einstein equations naturally split into dynamical equations and constraints, and these have different characters, so you cannot easily solve them altogether. So for instance, in the time-dependent case, what's usually done is one finds initial data to the Einstein equations by solving the constraint, and then you know that the dynamical evolution preserve the constraints. So if the constraints vanish initially, they will vanish to the future. But finding a stable way of doing that in the dynamical situation has taken 30 years. So that's hard. In the stationary case that's relevant for this talk, again, this has only been understood very recently. And the way to do it is instead of choosing a particular gauge ab initio, one implements a covariant gauge fixing at the same time as you solve the Einstein equation. So the idea is that instead of solving the Einstein equations, we solve this modified set of equations where we add this vector piece to the Ricci tensor, and this vector piece is constructed by taking the difference between two connections. One is the Levi-Civita connection associated to the space-time metric that we're trying to find, and the other one is a Levi-Civita connection associated to reference metric that lives on the same space-time manifold, but as a reference metric need not solve the Einstein equations. So why this is mathematically and numerically more convenient? So mainly the reason is that these modified set of equations have a definite character. So that means that the highest derivative terms in the equation have this very simple structure. So for the time-dependent case, this has the same structure as the standard wave equation. For the stationary case, this has the same structure as, say, the Laplace type equation. So therefore one can use standard techniques to solve these equations, even if they are nonlinear. But of course, we are not solving the Einstein equation, so solutions to these harmonic Einstein equations are solutions to the Einstein equation only if this vector that we've added vanishes on the solution. So the question is how you go about finding solutions to the harmonic Einstein equations where this vector vanishes. And the way to understand how you can do this is to, for instance, look at the Bianchi identities. So the Bianchi identities for these harmonic Einstein equations reduce to this linear equation for this vector xi. So in the time-dependent case, this is just a linear wave equation. In the time-independent case, this is just the standard, say, Poisson type equation. So then it's clear what one has to do in order to find solutions for where this vector vanishes. In the time-dependent case, one chooses initial data for which this vector vanishes initially, and its time derivative vanishes initially. So this is equivalent to solving the constraint equations. And then, because this vector satisfies a wave equation, then it's guaranteed that this will continue to vanish to the future. In the elliptic case, this is slightly more subtle. And morally, what one has to do is to impose boundary conditions for which this vector vanishes at the boundary, essentially. Yes?
What is the difference between the hyperbolic and the elliptic case here?
What is the difference?
Yeah, are you talking about stationary and static, or is?
No, stationary is elliptic. Stationary means no time dependence, and hyperbolic is time dependence, but the structure of the equations are the same. So you can try to understand how. Well, you can do it in parallel if you want. I'm only considering the stationary case, but because the structure it doesn't really matter, right? Well, it matters. The only place where there's a difference is on how you will go about finding solutions for which this vanishes. In the hyperbolic case, then this is easy because you simply have to construct initial data for which this is satisfied. In the elliptic case, it's slightly more tricky, and you have to impose boundary conditions compatible with this vanishing at the boundary, but then proving that if you do that, then the solutions to the harmonic Einstein equations are Einstein metrics is non-trivial. But for static spacetimes, then with asymptotically flat, asymptotically AdS, or Kaluza-Klein boundary conditions, we could prove that this is enough to guarantee that this vanishes everywhere. In the stationary case, which is the one that I'm interested here, there is no such result. But because the equations are elliptic, you know that the solutions are locally unique. So an Einstein metric cannot be arbitrarily close in the space of solutions to a metric with this, where this vector is non-zero. So in practice, we can always go and check whether this vanishes on the solutions. And in fact, that's what we do. And for the solutions that I will present, this is true within numerical accuracy. Yes?
This vector becomes a killing vector in the elliptic case, is that correct?
Not necessarily. No. In fact, that's not true, right? Because on the solution, this is zero. So the vector is zero.
The elliptic case.
Yes. In the elliptic case, so in all solutions, xi is zero. Right. The question is how. No, yeah, but that's the point. So in the elliptic problem, you can only essentially impose this at the boundary, but then of course it's non-trivial that this then is true everywhere, right? And that's, in the static case, that's what our theorem guarantees.
You're saying that you're anyway picking only the ones where it's
non-zero
everywhere.
Exactly. So because only for the ones where this is zero everywhere, then the solutions to these equations are in fact Einstein metrics, which is what we are interested in.
And in the hyperbolic case, if you start from the zero profiles,
yes,
you should obtain simply zero.
Yes, that's right. That's right. And the advantage is that, yeah, so what you say is true, and the advantage is that basically then all you have to do is to solve wave equations. And it is non-trivial that the Einstein equations, so basically this is what guarantees that if you choose this initially, this will be true later on. But that's the fact that this happens is non-trivial in the context of the Einstein equations, because these are nonlinear equations and singularities can occur. So.
Okay, but finally, the result will not depend on time?
No. So one thing is the time-dependent case. So if you start with this initially, then you evolve the equations, and this is true at any future time. So this means that in the hyperbolic case, if you do that, then solving these equations is doing exactly the same as solving the Einstein equations. Okay, even though the equations, if you write them down, they are not the same. But the fact that this is true is non-trivial, and that's a consequence of this equation. And you have to prove that this is going to be true everywhere to the future, and that's not trivial. But solving these equations turns out to be more convenient than solving the Einstein equations, because these are just wave equations, and we know how to solve these kind of equations.
The reason you add this vector field is because the cosmological constant destruction.
No. This hasn't, like I said, this has nothing to do with the cosmological constant. So the reason why we want to use this vector is because we want to change the two-derivative structure of the Einstein equations, because it's a bad derivative structure from a mathematical point of view. So the cosmological constant term has no derivatives. So for this discussion, it's not important, the fact that there's a cosmological constant. Okay?
I have related questions.
Sure.
To understand that. In Einstein equations, there is a wrong sign in front of the trace term, right?
Yes.
Is this what you're flipping by introducing this additional?
Well, actually, you do slightly more than that. You cancel that term altogether. So essentially, the crucial thing is having the Christoffel symbol here, because when you hit these with this derivative, then you kill the trace term that you say, and another two-derivative term which comes also with the wrong sign. And in the end, you end up just getting this nice wave-like structure. So you have three two-derivative terms in the Ricci tensor. And essentially, yeah, so you add that term to precisely kill the other two. Well, actually, the first one to do it was Madame Choquet-Brouat in the 50s that proved that the initial value problem for the Einstein equations is well posed. And then Franz Pretorius, well, Garfinkel first, and then Franz Pretorius did in the dynamical case, and Toby Weissman and collaborators implemented this same trick in the time-independent case. But that's like 3-4 years ago. Okay, all right. So, if we want to construct black rings, so what is that we have to do? So, again, we want to construct stationary black holes, so no time dependent. So these are in 5 dimensions. So in 5 dimensions, you've got 4 spatial directions, which we can split into two planes. In each of these planes, we want to preserve rotational symmetry. So in one of these planes is where the S1 of the ring sits, and we want the ring to rotate along this direction. In the orthogonal plane, we have an S2, and we also want to preserve the rotational symmetry of the S2. Okay? So the domain that we have is of this form. So somewhere in the interior of the AdS spacetime will sit a ring with this topology. So the actual domain, as you can see from this cartoon, naturally has 5 boundaries, namely the asymptotic infinity, the AdS boundary, the axis of rotation, and then the 2 poles of the S2 of the horizon and the horizon itself. So this has 5 boundaries, so essentially this implies that one cannot choose a smooth coordinate system which covers this domain in a single, one single coordinate system. So what we'll have to do is to use 2 coordinate systems. So we divide the geometry into 2 regions. So one, which I will call the far region, and it's defined because in this region, the vector which is tangent to the horizon never becomes null, okay? And then on the other hand, we have the near region, which will cover the neighborhood of the horizon, and it's essentially defined by the fact that this vector becomes null precisely at the horizon, and this constant that we have in here is the angular velocity. So then what we do is we choose adapted coordinates in each of these 2 regions. So in the far region, we'll choose coordinates which are adapted to cover the near boundary region, say near the boundary of AdS, whilst in the near region, we'll choose coordinates that are adapted to cover the near horizon region of the ring. So then, in order to have a well-posed problem, we have to transfer information between these 2 regions, and the way we do it is that in the region where these 2 coordinate patches overlap, we can use the values of the functions from one patch to give values to the functions that sit at the boundary of the other patch. Okay? There's another way to do it, which is to choose patches which do not overlap, but only essentially intersect along the line, and then you can impose continuity of the function or the first normal derivative. But we found that this was easier to implement. So the way to do it is the following. So in the far region, we write down the most general metric, which is close under diffeomorphisms that preserve the symmetries that we want to preserve, namely time, translations, and rotations in this direction and this other direction. So here, these functions t, a, and so on and so forth are unknowns, and if you set them to 0, then this is just a metric of global AdS, okay? So this is the far region coordinate, and we'll cover, and in these coordinates, basically the domain looks like this orange rectangular region, where all these green corners, these boundaries, so these are the boundaries where we impose just standard boundary conditions like regularity at the poles of the S3, and just we fix the metric at infinity so that the boundary metric is that of the static Einstein universe. So you see that this patch extends some region up to in the interior of AdS, but it doesn't cover everything. So here, these pink dots represent the region which is covered by the near region patch, and you see that they overlap in some region. So in order to provide values of the functions along this boundary, we just interpolate the values of the functions in this other patch. And we will do the same for the near region patch. So the values of the functions in the near region patch on this boundary are obtained by simply interpolating the values of the functions in this patch. Okay?
Well,
yes?
I haven't understood the project. Is it like a equi-variable?
So this is the domain. So our coordinates are R and A. R is a radial coordinate, so and A is an angular coordinate. So this is basically the region covered by our coordinate. So this is a coordinate.
Is there a significance to the shape? I can see some lines going like that.
Oh no, this is no significance. This is just our choice of coordinate.
Okay.
So it's not a coordinate invariant plot, so that's our choice of coordinate. So in the near region patch, basically, the domain looks like this. So again, so in here the metric, again, so we have different functions here. So our domain is this funny shaped region. Again, the boundaries, just say the poles, the axis of rotation, the poles of the S2, and the horizon. And here we impose just standard boundary conditions. So here, because we want to cover the near horizon geometry of a ring, we use the actual values of the functions for the known asymptotically flat ring. So these are all these functions with sub-zero. So T0, this is a known, analytically known function of the asymptotically flat ring. So we essentially address the asymptotically flat ring. So again, so in these near region coordinates, then the far region patch looks like, say, a polar patch. So again, they overlap in some region, and the values of the functions are obtained by simple interpolation. Okay, and you can change coordinates from one patch to the other by just a very simple coordinate transformation. And as you can guess from these plots, these are essentially related by Cartesian and polar coordinates, essentially. Okay, so the coordinate transformation is analytically known and very simple. Okay, so something else that we have to do in this business is to come up with a reference metric, because that's this is essentially fixes our gauge. So we have to construct a metric in this manifold, which satisfies all the boundary conditions, but as I said, it did not solve the Einstein equations. Okay, so essentially what we do is we set to 0 all our unknown functions, either in the far region and in the near region. And because the metric is a tensor, we can just add two tensors together, and we multiply each of these metrics by some interpolating function. Okay, that's an easy way to construct a reference metric on this manifold. It's certainly not the only one, and probably there are much clever and better ways of doing it. But that's what we used.
What determines the choice of functions?
I was going to discuss this. So the only thing which is important, or we found that mattered in terms of constructing the solution, is that this interpolating function had to vanish. So this is, first of all, this is a smooth function in terms of this coordinate row, which is this coordinate row covers our whole domain. So the only thing which was important for our construction is that the normal derivatives on each of the boundaries, so sufficiently large number of normal derivatives of this function vanish at each of the boundaries. So essentially at infinity, we required that this function had to have 4 vanishing derivatives at least at the boundary of AdS, and similarly this function had to have like 4 derivatives vanishing at each of these boundaries. And you see that this function, this interpolating function, looks very flat near each of these boundaries, and also near infinity, which is a point in these coordinates. Okay, so that was the only thing which was important. The other thing which was important was that this has to be smooth, sufficiently smooth. But other than that, surely there are infinitely many other functions which have these requirements, and if you come up with some other, the results should be essentially the same. Okay, but like I said, this is surely not the only way to construct a reference metric. That was just one way, a simple one. Okay, so which parameters have these solutions? So these solutions naturally have the parameters are the temperature, the angular velocity, and the AdS length. The temperature and angular velocity appear naturally as data that we have to fix at the horizon, and the AdS length is the AdS length because we are in AdS. So we can freely rescale our solution and set the AdS length to 1 if we want. Okay, so then there are only 2 physically meaningful dimensionless parameters, which is dimensionless temperature and dimensionless angular velocity. So in order to explore these black ring phases in AdS, what we did is we fixed certain representative values of the temperature, and then for each of these values of the temperature, we just varied the angular velocity. Okay. Then we solve the equation numerically. In this case, we use finite differences. And well, if anyone is interested, I'll be more than happy to discuss the details of how we actually solve the equation numerically. Okay. So before I go on to discuss the physics of black rings, are there any questions? All right. So let me discuss the physics of black rings. So first of all, I will discuss the thermodynamic properties of black rings. So as I said, we fix the temperature and then vary the angular velocity. So we shall be working in the grand canonical ensemble. So what we will do is that for a fixed temperature and angular velocity, which black holes exist, or which black holes exist. Okay. So let me first remind you about the thermodynamics of black holes in AdS in the static case. Okay, so no rotation. And in the static case, if we now plot, say, the free energy against temperature, well, this is inverse temperature, is well known that at sufficiently low temperatures, the only solution to the Einstein equations is within, say, the symmetry class, is just thermal AdS. Okay? Now, as you increase the temperature, at some point, you start having black holes. So black holes only exist in the static case above certain temperature. And above a certain temperature, this temperature here, then the black hole phase is the dominant one. So black holes in AdS at fixed temperature exist into 2 families, say the big black hole and the small black hole, because one is big compared to the radius of AdS, and the other one is small. And it turns out that above this temperature, which is known as the Hawking page temperature, the big black hole is the dominant phase. So the small black hole is always subdominant and doesn't play a role in the thermodynamics. Now, this temperature, so at this Hawking page temperature, there's a first order phase transition between thermal AdS and the big black hole, and Witten interpret this first order phase transition from the field theory point of view as a confinement-deconfinement phase transition. So at low temperatures, thermal AdS is a dominant phase, and that represents the confined state because the free energy has order 1 degrees of freedom, which is 0 in the gravity limit, whilst at high temperature, the free energy has order n squared degrees of freedom, and that's represented by the fact that you have a black hole in there. Okay? So now we will add rotation to this picture. So we'll be working in the grand canonical ensemble. So what one finds is that at temperatures above the Hawking page temperature, then the picture in the grand canonical ensemble is pretty much qualitatively similar to the picture in the static case. So we have a big black hole which dominates. That's this line here. It's big, so it's represented. So you see that the area is large in AdS, in units of AdS. You've got a small black hole which is non-zero, but it's very small, so you can't see it, and it's subdominant, and that's represented over here. So something to note is that for the big black hole, the angular velocity is always less than 1 in these units, whilst small black holes exist for all angular velocities, including angular velocities greater than 1. And I'll comment on that later in the talk. As you lower the temperature below the Hawking page temperature and above this temperature, you still have 2 black holes. But now, again, the big black hole only dominates for values of the angular velocity above a certain critical value, and there are no black holes below certain angular velocities. Okay? Again, the small black hole is irrelevant from a thermodynamic point of view, and the big black hole is a dominant phase above this angular velocity. And it's always less than 1. And if you keep decreasing the temperature, then the large black hole phase disappears altogether, and you only have a small black hole. And now the angular velocity of the small black hole family must be greater than this value of 1. Okay?
This is true for all. I mean, you don't have to separate your analysis in a slowly rotating and fast rotating.
No. So if you want, so for small black holes, they are below this temperature. They're always rotating fast, and below this temperature, they can rotate slowly. I'll comment on the significance of that later on. So this can be summarized, this discussion of black hole thermodynamics can be summarized in this plot. So here I'm showing the area. So this area is covered. This is the allowed area for black holes, rotating black holes in AdS. So this curve here is the static black hole line, and you see that they only exist above this critical temperature, that's the Hawking page temperature, and here you've got the big black holes, and below this curve are the small black holes. So here the colors in this plot represent the grand canonical potential. So this is essentially, so this is the subdominant phases, these are dominant phases, these are all black holes. That's the limiting angular velocity. So that's 0 here, and that asymptote to 1. So the angular velocity changes from 1 over here to 0 over there. So big black holes, the dominant phases, only exist to the right of this curve. And the small black holes only exist to the left of this curve and below. And like I said, I want to emphasize that they exist for all angular velocities, for as long as the temperature is low enough. Okay? So the question is, where do black rings sit in all this picture? So this is where black rings sit. So this is a representative temperature of whatever, but it's true for any non-zero temperature, even as small as you want. So black rings always sit above the small black hole. So that's the small black hole curve. And so therefore, black rings are, in AdS, are thermodynamically irrelevant. They're never the dominant phase. And the angular velocity is always greater than 1. Okay, that's the limiting value. So from a thermodynamic point of view, black rings are always thermodynamically unstable, and they never dominate the grand canonical ensemble. And in a very concrete sense, thermodynamic sense, they behave like small black holes in AdS. Okay. Now, what's important about this omega equals 1 limit? So one can see that for omega L greater than 1, the dual CFT is rotating at a speed which is greater than the speed of light. So that might make you suspect there's something genuinely sick about these states. And in fact, one can argue from the gravity point of view that black holes in AdS with an angular velocity greater than 1 are always unstable under superradiance. So these black rings, and in fact all these small black holes with angular velocities greater than 1 are all unstable. So black rings are always unstable and never dominate the grand canonical ensemble. And so that's one of the conclusions of our work. Now, whether they are dominant in the microcanonical ensemble or they can be dynamically stable, that's a separate question that we have not addressed in this work. Okay? Now, that's as far as the thermodynamics of rings. I want to highlight the fact that what I showed before in this plot is true for any temperature different from 0. So rings, there is no separation in some, well, we'll see there's a slight difference in temperature, but as far as the thermodynamics is concerned, rings don't care about the temperature. Okay? They all have the same features, and these are like essentially like this small black hole in AdS. Okay, so let's now study the geometry of black rings in AdS. So how do they look like, and how different they are from the rings in flat space? So there are two ways to visualize the geometry. One is by just embedding the horizon 2 sphere isometrically into Euclidean space, and the other way is just to look at the radii of these two U1s that we have. So this can tell us how big the rings are in units of the AdS radius. So at high temperatures greater than this value, then rings, as in flat space, they exist in two families, thin and fat. So for fat rings, then the radius of the S1 is much larger than the typical radius of the S2, so the gravitational self-interactions are negligible. Whilst for fat rings, the hole in the middle is small compared to the thickness of the S2. So those essentially have the same qualitative features as rings in flat space, even though we constructed thin rings which can be quite large. So as you can see, that's the size of the ring on the plane of rotation, and this is, can be several units of the AdS radius. So here I'm also showing the rotating AdS black hole with the same temperature and angular velocity. So as you can see, on the plane of rotation, these rings are close to the boundary, and they do have some deformation, so they know that they live in AdS and not in flat space, but still the gravitational self-interaction is small because the hole in the middle is large compared to the size of the sphere. On the fat side, then in this limit, rings, as you can see, they look essentially like membranes. So the extent on the plane of rotation is orders of magnitude larger than the extent of the ring in the transverse directions, and the hole in the middle is small compared to the size, if you want, of the outer radius. So that's essentially the same as the fat rings in flat space. Now as you keep lowering the temperature, something interesting happens. So at sufficiently low temperatures, that is less than this critical value, it's not possible to construct arbitrarily thin rings. So the thinnest one that we found in this limit is these ones here. So you see, these are pretty close to this critical value of the angular velocity, whilst fat rings essentially behave in the same way. So as you can see, these rings, as you keep approaching this critical value, spread more and more on the plane of rotation, whilst they asymptote, so the thickness on the transverse direction asymptotes to a certain value, which depends on the temperature that you have in there. And on the other hand, these fat rings, again, they essentially behave in the same way as we had before. And as you send omega to infinity, what you find is that this hole in the middle closes in a singular way, and the black hole and the black ring asymptote to the same solution, and that's a naked singularity with a finite size of the outer radius on the rotation plane. And that's the same as in flat space. But in order to see what happens as you keep approaching this critical value, it's easier to see if you lower a bit more the temperature. And what you find is that these rings asymptote to a new solution. They have a new limit, which is a membrane-like limit, in which the hole in the middle is very small, as you can see from the embedding, and the extent of the S2 is large in units of AdS, but the thickness of the S2 is very small. So fat rings, again, as you crank up omega, then you are on the fat branch, which behaves as in flat space. But as you approach, so therefore the conclusion is that at sufficiently small temperatures, as you approach this critical value of the angular velocity, rings approach a membrane That's the same limit as the black hole in AdS approaches, again, as you get to omega equals 1. And you see that the hole in the middle here, so on the plane of rotation, this ring is huge. It has several tenths of AdS length, but the hole in the middle is tiny. And clearly, the ring and the black hole approach to the same singular solution. That's a different singular solution than the one you get in there. So here you can show that the horizon of this membrane is basically a hyperboloid times a circle, and that's different from the singular solution you get in this limit. So this limit of rings is new to AdS, and that's a membrane type limit. Yeah.
The embedded didn't look actually symmetric. There was some crosses. If you go back one, that's this cross there.
What cross?
Around the hole, the orange thing. The orange.
Oh well, this is no, it's the same. So it's well, I mean, this is just numerical noise if you want. So it's actually symmetric. Okay, so yeah, so just the very last thing is that, you know, can the CFT tell a black hole from a black ring? And of course, I mean, the answer is obviously yes. When you plot, say, any observable related to the boundary stress tensor, so just the energy density distribution of the energy density on the 3-sphere, then, you know, so that's the one corresponding to a ring, that's the one corresponding to a black hole. So these are certainly different. But I think we haven't explored more the sort of field theory side, and I think there'll be interesting observables that one could look at and see how they probe the topology of the black hole in the middle, so just say Wilson loops or entanglement entropy that seem to be very fashionable these days. But we'll leave that for future work. So let me finish.
So I thought you said the CFT side was always had to be unstable.
Yes. So that's absolutely true. So the CFT side is unstable. I think the problem is that some of these statements are made at weak coupling, right? These are so you can compute the partition function of just free fields in the Einstein static universe, and you see that when you approach this, say, omega equals 1 limit, then things blows up. But on the other hand, you know, in gravity you can go and compute things and everything makes perfect sense. There's nothing that tells you that it's problematic. So even though it seems to be sick, I don't know of any sort of crisp statement at strong coupling, like from first principle CFT calculation that tells you there's something fundamentally wrong. On the other hand, if you want to compute, say, the partition function, then these are all subdominant saddles. So in that respect, they are irrelevant. So let me just quickly summarize what I've said. So we've constructed black rings in global anti-de Sitter space. They are never the dominant phase in the grand canonical ensemble at high temperatures. Rings exist, we have the thin and the fat families as in flat space, but at sufficiently low temperatures. Thin rings don't exist. You have this other new limit, which is a membrane type limit, and these very low temperature rings can be, in fact, very large in units of the AdS radius. The CFT, clearly the observables can tell a bagel from a donut, but I think it will be interesting to understand a bit better, look at other observables like, say, Wilson loops or other sort of non-local observables. So another result is that all the rings we found, they satisfy this bound. This, from the gravity point of view, this implies that they should all be unstable under superradiance. The endpoint is not known. So I'll have nothing to say about this, but I think that understanding the stability and the endpoint of these instabilities, I think that's an interesting open question that we should leave for future work. So thank you for your attention.
Well, thanks very much, Pau. Maybe we have just time for one short question.
So you talked about this membrane type limit. So does it have anything to do with, like, P-brane solutions to supergravity, or it's just a formal similarity?
Well, no, I mean these are vacuum solutions, so no gauge fields or anything like that. Right. And it's not a similarity. You take the limit, these asymptotes to a membrane. to a black memory. Well, it's not a black memory strictly speaking because it's a singular limit, so the singularity is visible. It's not hidden behind a horizon, but it has the topology of something that you would call a membrane.
But it wouldn't correspond to any of the extended objects of a supergravity theory.
Well, I mean, if you charge this up, you can relate it to the supergravity, like D3 branes. In this case, the rings, you can relate them to D3, D5 branes with momentum along the S1 of the ring.
The ring is not, in this solution, it's not carrying any of those?
It's not carrying any of those charges. So this is a vacuum solution, just pure Einstein gravity. But you can, like I said, you can charge it up and you can then interpret it in terms of the D3, D5 P system.
And when you charge it up, your expression for the thermodynamic potential would also incorporate.
Yes, it incorporates.
Your conclusions may not.
Yes, so then and then you can. I mean, there are known supersymmetric rings in flat space. In AdS, it's not known whether there can be supersymmetric rings. There are arguments which suggest that there shouldn't be, basically because in order to have them to have a balance of forces, you need to have pressure, and supersymmetry forbids pressure. So it's unclear whether there are supersymmetric AdS rings.